And this was to do with the torque, which how do we intervene there? How do we sort that out?
Okay, well, you've all seen what the radio set does. It continually pulses the power relay, causing the display to flash, etc. And I've had this radio in before, thought I'd cured it, but obviously not. So we've spent quite a bit of time now trying to nail down the actual cause for this, and I've not managed to do it, but we have come up with a solution. So I thought, well, we'll look at the mechanism by which the radio set is turned on, and we're going to start actually at the PA. I've got to make sure that the what I'm pointing at is in the middle of the screen, as I've noticed this recording system doesn't always show when you convert the file from the recorded file to the what we actually put on the web. Has the same screen area, but here we go. So starting in the PA section, this is the power input, your 14 volts input DC, through the filters, protection diodes, and then through two parallel resistors of 0.02 ohms onto the main 14 volt bus, and the lines that are going vertical feed the PA. Here you see the PA and the driver, and the lines going to the left hand side heading for the main fuse, and also the through the fuse is the power relay. This is the power relay, the thing you can hear ticking, and that's driven on and off by this digital transistor DTC11. And we'll come back to how that's fired in a moment. The 14 volts is current limited by a 4.7 ohm resistor, and that line goes down to the connector leading to the front panel, and that particular signal is called HV. I'm not sure what HV stands for in Japanese terms, but we'll follow that route in a moment. The digital transistor you see here is energized by a signal from the front panel called PWS, or power switching, and we'll now move to the front panel and look how those two signals are connected. So here's the schematic of the front panel on this connector on the right hand side. Let's change pages again. Got to make sure that you actually click on it. So HV is here, and that line, if we follow it round, comes down to the bottom. Change pages again. Here we've got HV, and HV feeds a 5 volt regulator, IC5, and IC5 provides 5 volts to the main processor here, IC1. That same 14 volt line is used to provide a signal to IC3. This is the actual reset device, and it's this device that constantly resets the main processor up here. So the 14 volts is dropped by a potential divider, R2021, so you've got approximately 5 volts here. It depends on your battery voltage. Battery voltage, as you know, can vary between 12 volts and 14 volts, so it's not exactly 5 volts all the time. And the output line here goes up to the main processor and causes it to reset. And when you reset a microprocessor, it goes back to 0 and starts doing what it was doing before. Now the sole purpose of this function is to turn the radio set on, and if you look on the left hand side here, try and get it into the middle of the screen, this switch S3 is your power on off switch, and that is biased with 5 volts through this line, through R31, and that line goes into interrupt request 0. Now an interrupt on a microprocessor has priority, so whatever the microprocessor is doing, if an interrupt is fired, all the values of whatever it's doing are stored away, and the interrupt sequence is run, and then it goes back to doing whatever it was doing before. And the sole purpose of interrupt request 0 is to fire a signal going back to that power relay, and that signal is comes out this side, and it is, if I can see it, PWRS, or power switching. Here it is. So when the interrupt fires, this line goes high. If the radio set is off, this line goes high, and that PWRS comes out here, PWRS, through a resistance R163, and that goes back out to the PA department. So if we go back to the PA, just zoom that down. So PWRS is what we're looking for, and that is here. You can never see these things immediately. There we are, PWRS, that red line. Move this over, and that fires the digital transistor, which turns on the relay, and the relay then feeds the rest of the radio set with 14 volts. So what's actually happening is, as we press the button to turn on the radio set, the interrupt is fired, PWRS is made high, that turns on the relay in the PA, and before the whole thing can settle down, this little device down here is firing yet another reset, and another, and the whole thing keeps oscillating. As I say, I've not found the actual reason for this. I've changed this device, I've changed capacitors, I've checked resistance values, but I did actually come up with a solution that seems to work. And if we look at the board layouts, go down one to the actual, this is the back of the logic unit on the front panel, and what we're looking at here, if I can get it to the middle of the screen, IC3 is that reset device. The 14 volts comes in R22, R21, which forms a potential divider, dropping the 14 volts to approximately 5, and this pin is the output that pulls down the main microprocessor reset. I changed this capacitor, which is a timing capacitor. It's how long it waits before it fires the reset when you originally turn the set on, and I even tried to slow it down by increasing that capacitance, but it didn't work. But then I noticed these two pads, and although there's no mention of what should be there, and there's nothing on the actual hardware, I tried a 1 microfarad capacitance in here, and that seems to have done the trick, in that the radio turns on every time. The only noticeable effect of putting this capacitance in is when you press the button to turn the radio off, it takes a little longer to turn off. You've got to hold that button in about 1 second. And basically I've also noticed that the radio is voltage sensitive, in that if you try and turn it on with a voltage of 11 volts going into this radio set, it either doesn't happen or it starts flashing, but once you're over 11.5 volts it's all okay. And you would expect that, you wouldn't expect it to work from 11 volts. So we'll actually go off to the hardware now, and I'll show you those effects on the bench. Okay, so we're in the final stages. Turning on, longer press to turn off, turning on. Now, something that I have noticed, what I'm going to do now is turn it off at the power supply and let the power supply die away, and then turn it on at the power supply with the set already in the on position. not done it this time. If I leave it a little bit longer, I'll come back in about 5 minutes and switch it on at the power supply. So here's the radio, and I've let it rest 24 hours. Just turned the power pack on, so we got 13 volts available. And we're going to turn the radio on the front panel, and she comes straight on. And then turning it off, we have a slightly longer press, about 1 second, and it goes off. Let's do that about 10 times. So as I said on the previous video segment, I haven't found the fault. I have done a modification, and if anybody out there has had this fault and actually tracked down what it was, I'd be interesting to know. So with that, we're going to set up the RF testing, just check the set out from an RF point of view. The only thinks that 80 meters is down, the performance 80 meters is down. We'll check that out, and then we'll see about shipping it back to the owner. So stay with us. Okay, so we're on 80 meters, 3.6 megahertz, and the specification says that we should get 10 dB signal to noise, at least 10 dB signal to noise, with the preamp on, with the filter set to sharp, with an input of 0.16 microvolts or less, and that is actually 1.8 to 29.7 megahertz SSB. So we've got our signal generator at the moment set at 1.6 and sharp on that, and we're using the line level meter here. So if I go a kilohertz off channel, there's our signal, 0 dBm. And when we kill the signal, we're actually just going back on frequency, so the signal is still present. You can see that's better than minus 20. And if we go bring the noise up by increasing the sensitivity, so the noise output from the receiver with no signal present is minus 20 plus 3, minus 23, and when we go off channel, as you would get with a signal coming in at 0.16 microvolts, you get 0. So the signal to noise ratio is actually 23 dBs. So we're going to do that for all the frequencies, but I think we should find them all roughly the same, and we'll just check one or two other things and then box it up and get in touch with the owner. So all the receiver sensitivity figures worked out. The preamp makes about 10 dBs difference, so if you get to put the preamp on, your sensitivity is 10 dBs down roughly, but the test states that the preamp needs to be on and the filter narrow. Now just looking at selectivity, just going to test it on the one band, because you're really just testing the filter. So we're on top band, and it says if we move 2.4 kilohertz off frequency, then the response should be at least 6 dBs down. So what we're going to do is just jump that down. I don't know if you can read that or not, it's hard to tell from this side of the camera. But, that's what did I say, 2.4 kilohertz down, and instead of reading 0 as it was when you were in the channel, it's now reading minus 15, nearly minus 16. So that's a 16 dB drop in audio output for 2.4 kilohertz shift. on frequency. Just turn the preamp off, and obviously that's a lot quieter with a lot less output. So there you have it. We'll do the transmit next, and then apart from a calibration, it's got a bad EEPROM on 50 megahertz, but 50 megahertz performance is okay. I've measured that, and the problem with the EEPROM is the actual type needed is no longer available, and I'm a bit hesitant to put a chinky version in. I've been on to companies to see if we can buy just 2 pieces. I won't mention who, but most of them have said no, you either buy the full roll or we don't supply, so that's the problem. Okay, catch you later. Okay, so the TX power checks out on all the bands, and we're now just going to look at what's known as a 2-tone test, which looks at the linearity of the transmitter in SSB mode. And to do that, we feed 2 tones into the modulator, and those 2 tones should not be harmonically related, and each tone individually should produce the same depth of modulation as each other, so they're matched in the modulation depth, and they're not harmonically related. To look at the RF, we've put a Bruin bridge between the transmitter and a dummy load, and we're tapping the Bruin bridge onto the oscilloscope, which is over here, and the 2 tones we've chosen are 1200 Hz at 2 millivolts and 2500 Hz at 2 millivolts. So when we turn it on, the edges of the envelope should be sinusoidal, and the middle should be a crossover point of 0, and there you can see the result. So it's if you follow the envelope shape on the exterior, you see it's sinusoidal and it's fully modulated in the middle. So that proves that the biasing on the pair of output transistors is matched, and the linearity is good. So that concludes our test of the receiver. It's time to get it boxed up. What I'll do is I'll produce this video, give the owner sight of it. The EEPROM is still going to be a problem because I can't buy one. They're obsolete. I can go for something that looks very similar specification wise, but most people want me to buy a full roll, and I only need one. Quite happy to buy 2 just in case one's faulty. The problem with the EEPROM is it's got the calibration data in it, and once we take that out and put a new one in, we have to go through the cal procedure from start to finish, which is okay, we can do that. It's if that EEPROM doesn't perform as well as the old one, and it starts dropping data or something silly, and then we're stuck. You know, we might be able to put the old EEPROM in back into circuit, but it depends, you know, how cleanly we manage to get it out. Anyway, that's a problem between myself and the owner to discuss. So thank you for watching, and I'll catch you further down the channel.